Hello everybody, my name is Satoshi Hoshino. Today, I'm going to talk about reaching motion planning with vision-based deep neural networks for dual-arm robots. As you can see in this picture, dual-arm robots have been attracting attention from the viewpoint of factory automation. These robots are basically required to reach their hands toward the respective target objects simultaneously. Reaching motion planning is to find a series of collision-free configurations to grasp an object. The final configuration is calculated from the object position measured by using sensors. So, sensor measurements are used to build the C-space. In this work, therefore, we use deep neural networks to solve these planning issues comprehensively. Given an RGB-D camera mounted on top of a robot as shown in this picture here, object images are used as the inputs to the networks. Thus far, so-called view-based motion planners have been proposed. For these motion planners, first off, reaching motions are instructed by a supervisor as shown in this figure. And then, deep neural networks are trained through imitation learning. We have also introduced an object recognition process into the simple motion teaching and playback framework with that network training. In the teaching phase, as you can see in these robot views, the robot was instructed to pick and place the three types of objects. The robot simultaneously registered the joint angles and hand positions for each recognized object. In the playback phase, the robot again recognizes the objects and measures the positions with the head-mounted RGB-D camera. Depending on the object position, the robot changes the instructed motion by itself. As a result, the robot successfully achieved all the pick and place operations. The robot successfully achieved not only the pick and place operations, but also the box packing operations, as you can see in these two movies. However, the robot used only one right hand. So what we want to do in this research work is to develop reaching motion planners for dual-arm robots. For this purpose, convolutional neural network CNN is applied to the motion planner. Imitation learning is used to train the CNN. In the motion instruction phase, first off, reaching motion toward the target object is instructed by a supervisor. During the motion instruction, the robot registers the images and the motions as the inputs and outputs. After the instruction phase, network parameters of the CNN are optimized in the learning phase so as to predict suitable motion outputs for the image inputs. In general, imitation learning is highly dependent on the training dataset, and the instruction cost increases in response to the number of objects. Therefore, as shown in these images, we use a single object in the motion instruction phase. In this regard, however, because the robot is instructed to reach each of the hands toward the single object, it is difficult to predict a suitable motion for an image with multiple objects. For this image, the robot is required to determine a sole reaching target and ignore the other objects. The image with the target object is called a target object image. For these same objects close to each other, the depth becomes similar. In this case, it is difficult to extract the point cloud of each object through distance-based clustering, for example. For this challenge inherent in using a single camera, we propose to generate the target object image through instance segmentation and reaching order classifier. Once the target is determined, the robot plans the reaching motion. Here, let us explain our approach to generate the target object image without using depth information. From the RGB image, each of the object is separately segmented through instance segmentation based on mask CNN. A single object is segmented in each image. The segmentation image is further classified into the reaching order where the right or left-hand label, R and L. According to the index, the object with the lowest number is determined as the target. Finally, the objects in the corresponding segmentation images are merged together. This output is the target object image generated without using depth information. We further explain our original order classifier based on CNN. For this segmentation image, the appearance feature is extracted through the convolution and the pooling layers. From the extracted image feature, normalized probabilities for the order outputs are calculated through fully connected layers and the softmax function. Finally, R or L with the highest probability is classified into the reaching order for the object in the segmentation image. All the segmentation images are classified into the reaching order with the right or left-hand label. As for an object classified into R, the robot uses the right hand. According to the index, the object with the lowest number is determined as a target for the right hand. The target object for the left hand is also determined in the same manner. Here, let us explain the overview of the motion control procedure. From the RGB image with multiple objects, the target object image is generated. Before motion planning, the target object image is fed as the input to the grasping classifier. The robot grasps the object when the classified hand status is close. On the other hand, the target object image is further fed as the input to the reaching motion planner as long as the classified hand status is open. From the motion planner, the amount of movement of both the hands toward the target objects are derived as the outputs. So the hand positions in the next step are given. The robot then moves the hands to the positions. For this purpose, joint angles are calculated by solving the inverse kinematics problem, including self-collision avoidance. This control ends when both the hands close. In each control step, the hand status open or close for the image input acts as a trigger of the following motion planning. Once the hand closes and grasps the target, the robot is no longer allowed to control the hand. The target object image is used as the input to the grasping classifier. The image feature is extracted through the following convolution and pooling layers. After that, the flattened feature is fed as the input to the fully connected layers. The output layer is composed of three status: open, close, open, open, and open, close. For normalized probabilities through the softmax function, the hand status where the highest probability is the classification result. And the hand status, if the hand status is open, the target object image is further fed as the input to the reaching motion planner. In contrast to the order and grasping classifiers, the CNN predicts the motion outputs for the image inputs. The architecture has two branches in the fully connected layers to right and left hands independently. In doing so, the robot is enabled to control the right and left hands simultaneously for the same image inputs. For example, here with the two target objects. Each of the outputs from the two branches indicates the amount of movement of hand, delta in the X, Y, and Z directions. In this experiment, a dual-arm robot next stage, equipped with Microsoft Kinect, was used. On the workbench, a cylinder was placed as an object. In consideration of the motion range, the object was placed in 4 positions for each hand in the motion instruction phase. The robot was instructed to reach each of the hands toward the object one by one. As a result, 552 segmentation image inputs and annotated outputs were obtained as training datasets for the order and grasping classifier, and 1,556 training dataset was obtained for the motion planner. All the deep neural networks, Segment Basic, Moscow CNN, and other 3 CNNs were trained in the learning phase using these datasets. At the reaching task, cylindrical objects were placed as shown in these pictures. All the objects were close to each other. The objects represented as R and L were placed in the right-hand side and left-hand side, respectively. In each picture, the objects with the bold letters, for example, here and here, here and here, and here and here, were the first targets. In the left picture, 6 objects were placed in the positions, same as the objects in the motion instruction phase. Therefore, these positions were known to the robot. In the middle and right pictures, on the other hand, 6 and 4 objects were placed in the positions inside and outside the instruction area, unknown to the robot. As the reaching results, let us first focus on the target object images. As you can see in these figures, the target object images were correctly generated. It is noticeable that the targets were correctly determined even for the objects placed in the unknown positions. So these images were further fed as the input to the motion planner. These figures shows the top view of the reaching trajectories. The robot successfully reached the hand toward the target, as can be seen from the left and middle results. Especially this middle result indicates the generalization capabilities of the grasping classifier and motion planner enough for the task. For your information, the robot successfully reached the hands and grasped not only the target objects in this trial, but also other objects in the second and the third trials. In the right results, however, the robot stopped both the hands in the middle of reaching. This result indicates that the generalization capability was not applicable to the objects outside the instruction area. Finally, let us show you the demonstration movies. The cylindrical objects were placed in the known and unknown positions. From the RGB images, all the objects were detected and segmented. Each of the segmented images was then fed as the input to the reaching order classifier, and finally, the target object images were generated. These planning issues were all solved by applying the deep neural networks. Okay, so in the upper movie, we can see that the robot successfully reached the hand toward the targets and grasped the objects. In the bottom movie here, the robot also grasped the targets, even though the objects were placed in the positions unknown to the robot. Okay, that's it. Thank you for your kind attention.